In this video, we are going to discuss heat engines and learn about the second law of thermodynamics. And we actually already know the second law of thermodynamics. The second law of thermodynamics is the fact that heat flows spontaneously from hot to cold. And through this video and into the video with entropy is discussed, we're going to learn about why that has to be the case. Alright, so let's learn more about heat engines, which are going to obviously obey the second law of thermodynamics. So we're going to learn about what a cyclic process is. The cyclic process is one where the system after going through a series of steps returns to its original thermodynamical state. That means at the end, if you look at the overall process, the change in internal energy is going to be 0, and the change in some other mysterious term is going to be 0 as well. Alright, so returning back to the idea that the change in internal energy is going to be equal to 0 once the entire process is completed. So for a heat engine, you're going to take in energy from a hot source. So we're going to call this QH. You're going to turn some energy into work. So that's going to be work of the engine. And then finally, you are going to expel some of that energy so essentially whatever's left over to a cold source. So that's going to be QC. So we already stated that delta U is going to be 0, so using the first law of thermodynamics, we can plug in our 0 here, and the heat is equal to the negative of the work. We do have to change perspectives though, because we've been talking about the work on the gas, and we need to now talk about the work done by the gas, which would be the work of the engine. And Q net expands to QH minus QC, because the difference between those two is how much energy can actually go into the engine doing work. So rewriting it with this, get this equation here, where the work done by the engine is equal to the heat coming in from the hot source. Remember, this is in absolute values because I've already put the minus sign in here. And the absolute value of the heat that is expelled to the cold source. So this allows you to calculate how much work the engine can actually do. So mechanical work. We can actually then calculate the efficiency of the engine, so the thermal efficiency, by taking the ratio of the work done by the engine compared to how much energy was taken in from the hot source. So how much energy do you need to take in compared to how much work you actually get out. We can sub this relationship in for the work of the engine and reduce it to also get this relationship here. And because we're taking an energy divided by an energy, so joule divided by joule, efficiencies are unitless. You can actually multiply by 100 and turn it into a percentage. And engines are really not that efficient. Usually if you have 60%, it's a really good engine. Usually you see 30 to 40%. And not only do you lose energy due to something we're not really taking into account here, which is due to non-conservative forces like friction, but you're also losing energy because you always have to expel energy. You can never have a 100% efficient engine. And this is because we had two conditions for returning to the original thermodynamical state. And we've only addressed one so far. So we talked about this one, but we haven't addressed this yet. So we're going to stop and do an example problem, and then we'll come back in the next video and discuss what this is.